Good evening and welcome to all the eager viewers, সকল আগ্রহী ছাত্রছাত্রীদের আমরা স্টেপ আপ বেঙ্গল এর টিম থেকে স্বাগত জানাই। ক্লাসিক্যাল মেকানিক্সের পরবর্তী ভিডিও লেকচারে ডিউ টু বিজি শিডিউল we could not upload any videos last week. For that, we first say sorry to all. I hope that all of you are waiting for new topics because so far we have discussed about degree of freedom in lecture number 1 to 5. Those of you are new, please revise L1 to L4 of our classical mechanics lecture series. From there you can easily realize what is degree of freedom, and we have already discussed all the related problems on degree of freedom for CSI and NET. Now the question comes, what is the actual implication of degree of freedom? To realize the actual implication, we are actually indebted to these two persons. One is Leonhard Euler and the other one is his disciple or student, whatever you may say, Joseph Louis Lagrange, J.L. Lagrange. Think, what was the rich culture shared between both of them? Those two men were tremendously popular as mathematicians as well as physicists. In mathematics, we have seen Euler phi function or Lagrange theorem on group theory, on subset, or rather subgroup, Lagrange theorem on subgroup, or rather the order of subgroup. As you all know, order of subgroup. Mainly in mathematics, the most remarkable feature of his work was the order of subgroup. সাবগ্রুপের অর্ডারের উপরে কাজ করেছিলেন, এটা তোমরা সকলে জানো. All of you perhaps know what actually he did and whatever may be. So the rich culture, as I was talking about, given by these two famous persons, ultimately in future came to us as Lagrangian mechanics. Now, if we all analyze the total aspect, what was degree of freedom? Degree of freedom was in general 3n minus k in R3. That is the main feature, because in R2 we have seen also the representation, but the main feature will be this one, 3n minus k. So degree of freedom actually deals with the portion where there is no constraint. We have already seen there is no constraint. We have already seen that for simple pendulum. For details concept, all of you are requested to revisit our previous lectures, from where you can easily see how DOF for simple pendulum has been derived. So in simple pendulum, one constant equation was there, x square plus y square equal to L square, and we have configured that in our previous lectures. This is L, this is the position xy. So one constant, that means one equation is given where certain restrictions was imposed on the motion of that bob means small mass bob বলতে আমরা স্মল মাসকে বুঝবো তার উপর একটা রেস্ট্রিকশন চাপানো হয়েছিল one restriction was there this was the restriction total motion was in 2D so coordinate were x and y and one constant was there so total DOF that is equal to single part for a single particle this is one particle so in general 2 minus 1 constant 1. Now take a look at the beauty of the subject here. In Newtonian mechanics all the theories has been developed on the simple basis of the application of the fact of his second law P equal to mf which in our mechanics often comes to us as force is equal to m into dv dt. Some would like to write it as dv dt, that means the expression for acceleration, where some other would like to mark it as d2s by dt2 or in other notation v dv ds. These three notations are mainly used to derive all the facts from in Newtonian mechanics where the main principle is P equal to mf. But as I was talking about, the most beautiful thing of Lagrangian mechanics, which was in fact derived by Euler and Lagrange, those two mathematicians were heavily responsible, mathematicians as well as physicists. We are talking about Lagrangian mechanics. Lagrangian mechanics, they have avoided using this particular result, and in details we would see later how they formed their theory. But the most important part I was talking about was degree of freedom. In Newtonian mechanics, the constraints, that means free particle concept was used. Free particle concept. That means in Newtonian mechanics there was special importance to the particles which were free, say moving under gravity freely. But in Lagrangian mechanics, constraints come into play. Lagrange developed his theories, say in Newtonian system, say a particle has x1, x2, xn coordinates. In general, we take these coordinates from Rn, n-dimensional vector space Rn. Some call it as Euclidean space also. So total n number of coordinates, but if k constraints are there, then these coordinates may reduced to n minus k, and that is equal to total DOF, and that is equal to, as Euler and Lagrange both put a special stress, that total DOF, that is called generalized coordinates. Say we have three coordinates x1, x2, or say two coordinates, as in simple pendulum we are just visiting. Just two coordinates, one constant was there, so ultimately DOF was 1. So in case of simple pendulum, where in Newtonian mechanics these two are used, in case of simple pendulum we have DOF equal to 1 DOF. So here the generalized coordinate is Q1 as mentioned by Lagrange himself. Generalized coordinate was Q1. So in general, the free portion, that means total DOF, ultimately equal to number of generalized coordinates, and they are in general, say this type, say here total m number of coordinates in Rm, say m may be 2 or 3 or 4, etc., whatever it may be. Say generalized coordinates, that means depending upon the DOF, these numbers, say 5, x1, x2, x3, x9, these 9 coordinates say are there, and among them only 5 are free. That means DOF equal to 5. So Lagrange proposed those as generalized coordinates and marked them as Q1, Q2, Q3, Q4, Q5. আশা করি সবাই বুঝতে পারছো যে এই পাঁচটা আলাদা আলাদা কোঅর্ডিনেট উনি তুলে নিলেন, whereas কটা ছিল? টোটাল 9. But in Lagrangian system, generalized coordinates were introduced. He just considered the portion depending upon degree of freedom. So ultimately this is of the form Qi, where I may be 1, 2 up to finite in terms. So this is generalized coordinate. So from now on, whenever we see this quantity, this is ultimately coordinate. Say in Cartesian system, if in Cartesian system we consider, then Cartesian system, how many Qi are there if the particle is free? That means Q1, Q2, that is very similar or equivalent to x, y in 2D. In 3D, Q1, Q2, Q3, if the particle is free, here it is also equivalent to x, y, z. Clear? So ultimately in 3D or 2D, these are Cartesian system. If we consider polar system, then Q1, Q2 will be very similar to r, theta, and this is two-dimensional polar, and three-dimensional polar system we would later come that r, theta, phi, 3 coordinates, those are equivalent to Q1, Q2, Q3 if those particles we are considering are free. But if some constants are there, say there are one constants here, then there will be, say phi is fixed, phi is say 60 degree, this is a particular angle, we will see later. ধরে নিচ্ছি এটা 60 ডিগ্রি, তাহলে সেক্ষেত্রে ফ্রি অংশ এটা, সেক্ষেত্রে তার জেনারেলাইজড কোঅর্ডিনেট দাঁড়িয়ে যাবে Q1 আর Q2. So in general, generalized coordinates, this is important point for CSIR or such exams to realize. Generalized coordinates in general are denoted by Qi, and in general they are of the type distance or angle or some quantities dependent on these two, basically distance and angle. In Cartesian, x, y, z, or in general xi type distance, maybe it may be r, because r is also a distance, as we know, r equal to root over x square plus y square in 2D system. As we all know, সবাই তোমরা জানো যে একটা পার্টিকেল যদি এভাবে চলে তাহলে তার এখানে পয়েন্ট, that the coordinate of this particular particle is xy, this is y, this is x, and from origin it is at r distance, so r means root over x square plus y square in 2D. In 3D, obviously r will be root over x square plus y square plus z square. These are the results all of you know from 3-dimensional or 2-dimensional geometry, etc. But in general, these are distance functions. So in our theory, when we handle all the questions of higher level maths, then we see that these coordinates are mainly of qi type where they may be distance or that same qi may be angle. Angle, what is mean by angle? Theta, comma phi, comma say other angle psi, etc. So in Lagrangian mechanics, by qi we denote distance or angle. Distance or angle. Now, if we look about Newtonian mechanics, there the system is very much similar P r theta. Take a look at the beauty. In Lagrangian system, this same particle will be q1, q2. This is the beauty of Lagrangian system. Here, r was distance and theta was angle. So, in general, r was used to imply distance whereas theta as angle, but Lagrange imposed a generalized condition to describe those coordinates as q1, q2, etc. So these may be of the type distance or may be of the type angle in general, or maybe some other quantities depending upon these two, but that portion is not asked even in CSIR. So we should put special importance in the fact that qi should in general be either distance or angle. Clear? I hope up to this portion all of you have good idea about generalized coordinates. Next comes, if we describe generalized coordinate, then what will be its derivative? This is important. As we derive Lagrangian mechanics, then we have to know the derivative of generalized coordinate. These derivatives are in general done by partial differentiation. By partial differentiation আমরা এই ডেরিভেটিভ গুলোকে খোঁজ করতে চাই। সেটা কি রকম হবে? Say we have to differentiate q1, quantity q1 with respect to q1 partially. Then what will be the expression? Del q1 divided by del q1. Someone writes this as del q1 of q1. Now this is clearly 1, but take a look at the beauty. If we differentiate del q1 with respect to another coordinate del q2, say q1 is our r and q2 is our theta, then if we differentiate r with respect to r, we will get 1, but if we differentiate r with respect to theta or theta with respect to r, then what will we get? q2 of q1, and that is equal to 0. Say here, if we want to derive del theta of r and theta are in general independent, so this will be 0. So this is a famous research work done by those two famous persons to come to a point that whenever we have partial differentiation of del qi with respect to del qj, it may be of two types. Either it may be 1 or it may be 0. When it is 1, when I equal to j. When it is 0, when I not equal to j. Say here, just see here in the previous page, del q1 by del q2. Here I is 1, j is 2, so the result is 0. But here I is 1, j is 1, so the result is 1. These two results actually abbreviated as, someone writes it as delta ij, or in sometimes we see it as delta ij. This is Kronecker delta, Leopold Kronecker delta. This delta is called Kronecker delta. Its value may be 1 or may be 0 depending upon whether I is equal to j or not equal to j. So ultimately Euler and Lagrange used this particular use of delta ij or this delta ij same to point out the fact that whenever we take partial differentiation of generalized coordinate del qi with respect to del qj, only two answers are possible. One is 1, the another one is 0. Clear? Then next we come why they have then comes the point why they have taken partial derivative. We have in our hand Newtonian mechanics already, and we are learning Lagrangian mechanics. So in Newtonian mechanics, coordinates are in general denoted by xy or xyz or r theta, etc. So in Lagrangian mechanics, we have already the idea qi of qi clearly. Then in Newtonian mechanics came the second block, that was velocity. What was that? Just simply time derivative of x, that means this coordinate, or maybe y, that means dy dt. So to derive velocity, Newton simply used time derivative on the coordinates. So if in Lagrangian system we have the idea of velocity, then we must have this partial differentiation, because here the coordinates are in general q1, q2, q1, q2 dot 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 qn up to qn. So to make such a comparison or to derive the velocity, this particular partial differentiation was done. And velocity, how they derived it? Say, here this was denoted by x dot by Newton himself, this was x dot, this was y dot. As we all know, time derivative are represented by dots. Very similarly, in Lagrangian system, qi was the coordinate. So it's, if we take dot, then what will be that? dqi divided by dt. So this is called, here this was called velocity in Newtonian system, but here we should have all the results on generalized coordinates, or rather depending upon generalized coordinates. So this term is called generalized velocity. First generalized coordinate qi, then generalized velocity qi dot. Clear? And that is dqi by dt. So in this particular video, we have briefly discussed about how DOF was used, or the concept of DOF was used to derive generalized coordinate system, and then finally how to use those generalized coordinates to derive the expression for generalized velocities. In our next lecture, we will see how those two famous persons produced one after one magics to develop all the results of Lagrangian mechanics, which are very much important for CSIR exam. So I hope all of you have understood today's lessons properly. Just revise it with the previous lectures and like our video if we have done anything recommendable, or share it with your nearby friends. So until we upload new videos, we hope that we can upload new videos regularly from now. Goodbye from our team.